Hey, what's up? It's your old pal, Mr. Cook. We're going to go through the Unit 7, Part 2 test review. So this is about McLaren series, Taylor series, error, and, just in general, power series, interval of convergence, and all that stuff too. But you're not in this fight alone. You're going to be able to go through this test with this nice little review sheet. And it'll be helpful to use, especially for this stuff when you have the Taylor expansions and this list of general terms for the Taylor polynomials, or Taylor expansions or something, Taylor series or something. So we start off with this function, 1 over x to the 5th power, g of x equal to 1 over x to the 5th power. We do have a typo on this. It says find the Maclaurin series, but obviously we can't center this at 0, right? Just simply because at 0 for x, 1 over x to the 5th power, this is going to be like a value that we're not allowed to use, okay? So even on if you look over on the formula sheet, there is a formula that fits exactly to this 1 over x. It uses some power, but it's going to be centered at 1 instead, for this. So we got to kind of concede that. But we do have this pattern. It's a little hard to see. I'm sorry about the pixelation on the document that I have, but it looks like this: 1 minus x to the n times negative 1 to the n power. And that's if the x value is used with 1 over x. So luckily, if x is the value that we're using, we can actually just plug that in, for the x value that we're using over here for our center. So this can become g of x is equal to 1 over x to the 5th, which is the same as saying this infinite series, n equals 0 to infinity, of negative 1 to the power of n, and then x to the 5th minus 1 to the power of n. So we can just use the basic rule to write that out. In fact, once you notice the pattern, you can take whatever the inside part is and just put that in as x. So for example, sine, sine is going to use this rule over here. So, and it says negative 1 to the power of n, x to the power of 2n plus 1 over 2n plus 1 factorial. So that is going to be the general term that we're going to use for this. So we just copy it over here. So g of x is equal to sine of 2 minus x to the 3rd. And remember that the pattern that we're going to use for the Taylor series goes from negative 1 to the power of n, and then whatever our x value is to the power of 2n plus 1 over 2n plus 1 factorial. And yeah, sure enough, this is our input, so we're just going to put that in here, 2 minus x to the 3rd power. And, that's what we're going to use. And then let's see, does it ask us for anything else? No, just use the powers. I was going to see if they wanted us to find like radius of convergence or something like that, but it's just find the general term for it. Okay, 1 over 3 plus x squared. You can do this one of a couple of ways. You can just define it as 1 over x, the same as before, and then just use this as the input. That's probably what I'd end up doing here. Let's see if there's a better option. Nope, that's it. I wouldn't even use this one, but technically you could actually use this one as well, and I'll show you how to use that one in a second. No, let's just keep it simple. Let's just use the one that we have there, 1 over x. But I do want to point out that there are many different ways to find these series. These are just the easiest way to find it. And again, recognizing that like this first one is not Maclaurin, is not centered around 0, because that's not possible. Anyways, so if we use that exact same power, and again, this is going to be centered around 1, we end up with the following. So this is going to be the series n equals 0 to infinity, and then it'll be negative 1 to the power of n, and then x minus 1. So the x value is 3 plus x squared in this case, minus 1 to the power of n. Notice, again, we just use the same rule right here. And wherever we see the x value, we just plug in our input, which is 3 plus x squared in this case. And then we just, we can simplify it a little bit. 3 minus 1, that just gives me a 2. And there you go. There's the series. Okay, so that's the first 3. Now we move on to the next one. Let's see. Write the first 3 non-zero terms of a power expansion for the given function. Use the basic power series list again. Okay, so this is just asking us to write the first three terms. That's not a big deal. We again just use the rules that we have here, cosine and sine, and then we plug these inputs in for the x. So for cosine, oops, sorry about that. Cosine is going to be equal to n equals 0 to infinity of, 0. I think that would be 0. Negative 1 to the power of n, and then it's x to the power of 2n over 2n factorial. And where did I get that from? Well, that's just the cosine rule over here, but not pixelated, obviously. Okay, but then wherever we see an x, we're just going to put this input. So we're going to do that. Put it on in there, 3x to the 5th power. There we go. And there we are. And then it says to find the first three non-zero terms. So we can just plug in 0, 1, and 2. And that's it. That's the first three non-zero terms. So let's plug in 0 for n first. So we get negative 1 to the 0 power, 3x to the 5th to the 0 power again, over 0 factorial, plus, and then the next term, if I plug in 1, I get negative 1 to the first power, 3x to the 5th power, to the 2 times 1, which is 2, over 2 factorial, because 2 times n, being 1, is going to be 2. And then my last term that I get is going to be negative 1 to the 2nd power, 3x to the 5th, to the, I'm plugging in 2, so 2 times 2 is 4, so 4th power over 4 factorial. And you can just leave it like that. I think the answer key might have this simplified, but you don't need to do that. Okay, and then same thing for sine. So I use the sine pattern now, n equals 0 to infinity. And, that sine pattern looks like this, negative 1 to the power of n, and then x to the power of 2n plus 1 over 2n plus 1 factorial. And our x value, our input, is just going to be that, 4x minus 3. Okay, there we go. And again, they just want the first three terms, so we can just plug in 0, 1, and 2. That should be the first three terms. So if I plug in 0, I get negative 1 to the 0 power, 4x minus 3 to the 0 power plus 1, so that's the first power, over 2 times 0 plus 1, which is 1 factorial. My next term that I'm going to use is n equals 1. So if I let n equal 1, it's going to be negative 1 to the first power, and then it'll be 4x minus 3. And then 2 times 1 is 2, 2 plus 1 is 3, over 3 factorial. So it looks like it's just going to be the odds. So the next one is going to be negative 1 to the 2nd power, 4x minus 3 to the 5th power, all over 5 factorial. And I should make sure that I'm not making any mistakes here. Instead of infinity, I'm just going to, since I only went up to 2, I'm going to put a 2 there because I want to make sure this equal sign is true. Okay, there we go. All right, there we go. So that's the first 5 problems. And let's see, can we do this one too in this video? Find the specified Maclaurin or Taylor polynomial. For these, you must use the Taylor procedure. Okay, so we have to use the Taylor procedure to find the Maclaurin polynomial for this. Okay, yeah, that's not an issue. So the Taylor procedure means that we have to use the Taylor polynomial, term. So the formula for that looks like this. It's f of n of c over, so this is like the nth derivative of c, some value c where it's centered around, over n factorial times x to the power, x minus c to the power of n. All right, and then since it's Maclaurin, that means that the c value is going to be equal to 0. So that's, let's just go ahead and replace all these with zeros just to make our lives a little easier. And x minus 0 is just x, so that turns into just x to the n. There we go. So that's the Taylor polynomial term, but it's simplified for Maclaurin series because c is going to be equal to 0. So that's the pattern that I'm going to use for sine of 3x. So in this case, I need to find the 5th degree Maclaurin polynomial that approximates this. So 5th degree means that I'm going to go up to n equals 5. Okay, so I start with 0. And I don't know if so different teachers teach this in a different way. I always do this in the following procedure. What I do is I start with my function, okay, f of x, and then the first thing that I do is that I take the, I take 5 derivatives for this because it says n equals 5, so I need to go up to the 5th derivative term. So I just do the first 5 derivatives real quick. F of x is equal to the first derivative. The derivative of sine is cosine, so I get cosine of 3x, and then the chain rule takes over and I get a 3. And then the second derivative, I take the derivative again. The derivative of cosine is going to be negative sine. So I get a negative sine of 3x. And I get, I have that 3 there. And then I get another 3 from the chain rule here. So, it's going to be 9 or 3 squared. And then the next one that I get, so the third derivative is going to be, let's see, the derivative of sine is cosine. So I get a negative cosine of 3x, and then I multiply by 3 because I have another chain rule. And 3 squared times 3 is 9. 3 squared times 3 is 3 to the third power. So do you see what's happening here with these patterns? The next derivative after that, so the fourth derivative. If I take the derivative again, now it's going to be a positive sine of 3x, and now it's going to be to the fourth power. And then finally, my fifth derivative is going to be 3 to the fifth power, and then cosine of 3x. So there's my first 5 derivatives. Next, I need to use the center value, so 0, and plug that in. So I'm right now constructing this part right here of my Taylor polynomials. So next I plug in 0. So f of 0, f prime of 0, f double prime of 0, f triple prime of 0. So the third derivative with 0 plugging in, the fourth derivative, and I'm going to plug in 0. And then the fifth derivative, and I'm going to plug in 0. All right, let's see what we get with all these. So sine of 0 is just going to give me 0. Cosine of 0 is 1, so I get 3. And then sine of 0 is still 0, so this gives me a 0. So it looks like every other one's going to be 0. Then let's see, the third derivative, if I plug in 0, I'm going to get negative 3 to the third power. 3 to the third is 27. And then I get 3 to the fifth power. So let's see, that's going to be a positive 3 to the fifth. Okay, so that's going to be 27 times 3, which is 81. 81 times 3 is 243. So I think that's 243. Okay, so we've got all these coefficient terms. Now, if I want the fifth degree polynomial, it's going to look like this. I do p with a subscript of 5 of x. So that means that the n value is equal to 5. And then I write out my terms. So it's going to go something like this. So it looks like on the n equals 1 term, or well, let me write out everything, okay? So I'm going to get, for the 0 part, n equals 0, I get this part here, so that's going to be 0 over n factorial, so that's going to be 0 factorial, and then times x to the 0 power. That's like the first degree part, okay? And then I just keep using like these coefficients here as the numerator, so the next one's going to be 3 over something, and then x to the first, and then 0 again, so 0 over something, x to the second, and then negative 27 over something, x to the third, and then 0 again for the fourth term, so plus 0 over something, x to the fourth, and then finally 243, so then plus 243 over something, x to the fifth. And then that thing that goes in the denominator is the n value factorial, right? So 1 factorial, 2 factorial, 3 factorial, 4 factorial, and 5 factorial. But the nice thing about this is that anytime I have this 0 in the numerator, that's just going to be 0 overall. So I can just eliminate those terms. So all the even terms, it looks like. And then we get this nice polynomial approximation. That's a fifth degree polynomial, and it'll look pretty close to sine of 3x. So here's how I like to write it up afterwards. The function f of x equals sine of 3x is about equal to a fifth degree polynomial approximation that fits these 3 terms. It's going to be 3 over 1 factorial x minus 27 over 3 factorial x to the third plus 243 over 5 factorial x to the fifth. And there you go. You can just leave it like that, and that would be the approximation that you would need for it. And that's what it's asking for. Find the fifth degree Maclaurin polynomial for that function. Okay, I think that's it for this video on the review. So going through number 6, we'll pick up where we leave off in the next video. All right, hope you found this helpful. If not, go find your math teacher, get some help. If you want some help from me, I'm Mr. Cook. I'm around in the morning and also after school. So just come and find me. Okay, thank you very much for watching. I hope to see you in the next video. Bye-bye.